All right, we are now recording. I'm going to get the slideshow set up for the current slide, though we're not going to be using it. But what I'll do is get my whiteboard up. And now I've got to deal with its taskbar, toolbar, whatever you want to call it. Get it as much out of the way as possible. Okay, now we'll move the whiteboard so I can get maximum white space. Okay, it looks like about as good as I could do. All right, any issues, problems, concerns, other things such as that? Still only got 6 people here. So how about this? Before the class is over today, remind me I need to make this announcement. Now, if any of you need to leave early, please let me know a few minutes before you need to leave so I can make the announcement then to get the maximum number of people exposure on it. So any questions, any issues, any concerns before we get started where we left off last time? All right, let me get my stuff here in hand. I think I'll get the book in my lap to begin with. It's too heavy to hold there for long, but at least it's easier to read. All right, what we talked about last time, and perhaps I should, because last time was so long ago. I hate to back off like this, but let me back off again and go back to the 7.4. Okay, and I thought I had already done from current slide, but evidently it didn't take. So let's go back a few slides. Here's the definition of arc length. If you have a function y is equal to f of x, and that function represents a smooth curve, no corners, no discontinuities, no cusps, nothing that's irregular about it. Very smooth curve on the interval from a to b. Then the arc length of f, of that function f, between a and b is given by little s, stands for arc length, okay? The integral from a to b of the square root of 1 plus the derivative of this function squared, okay, times your dx. Now, if you had it defined the other way, x is a function of y, g of y, then the arc length between c and d on the y-axis would have been the integral from c to d, 1 plus g prime of y squared dy. So there's our equations, our formulas for arc length. So let's get back to where we were. Okay, that's where we left off. So now we'll go to back to the whiteboard. So all of you have that firmly in your mind now. Okay. Okay. Example 2. Chapter 7, Applications of Integration, 7.4, Arc Length and Surfaces of Revolution. We're on page 476 in Chapter 7, and that's top of the page, Example 2. Okay. Find the arc length of the graph of, okay, for some reason my pen is not responding. Oh, there we go. Well, I thought it did. There we go. Here we have it. Here is your y, which you could also call f of something. Oh, f of x, of course, if it's y, is equal to x cubed over 6 plus 1 over 2x. Okay, on the interval. Whoa, here comes somebody, I can't read the name, Jose. I'm sorry, Jesus is here. Let me mark Jesus here. Hold the thought. Jesus is present. Okay. All right. Jesus, we're on in Chapter 7, Applications of Integration, Section 7.4, Arc Length and Surfaces of Revolution, on page 476, top of the page, example 2. I just was writing it down. So here is the function on the interval. This is a closed interval. That doesn't really matter much. 1/2 to 6. No, 2, sorry. 1/2 to 2. Okay. And there's a figure in the book. Okay. Now, I realize maybe some of you don't have the same book, but here is the figure. That's what it's looking like. It's a parabolic looking shape, though it's not a parabola. Okay. That is the graph of that function. See, we could have gone further to the left. You can't get to 0. That doesn't look like that's going to be possible because of that second term there, 1 over 2x. You certainly can't go there. So 1/2 is a good place to start, and it looks like you could have gone further if you wanted to, but why not stop at 2? So we're looking at the arc length just in that interval from 1/2 to 2. Nice, smooth curve. This should work. What's the first step you need to do? This question sort of has a Jesus answer. Oh, no, okay, I thought someone else was coming in. It's that silly window at the bottom. If y'all see anyone trying to get in, let me know, because sometimes I get carried away with what I'm doing and not paying attention to the bottom of the screen. Okay. That formula we looked at before, what did it sort of indicate? One of the first things you got to do. Sort of the Jesus answer in Cal 1. Take a derivative. Okay. Now before I take a derivative there, I can't get that equal sign to draw. There it is. Okay. I want to rewrite this function. Now, I didn't leave myself room enough to. I think I'll rewrite it this way. 1/6, it doesn't matter about this part, x cubed plus, oops, was that? No, I thought somebody else coming in. 2x, well, actually, I'm going to write it this way. 1/2 x to the minus 1. Does everybody agree that is the same function? I just pulled out my fractions, 1/6 x cubed plus 1/2 times x to the minus 1. Agreed or not? Okay, good. All right, now let's take the derivative. I think that second function is easier to take a derivative of. What would be its derivative? Okay, remember how to take a derivative. Okay. Exponent times coefficient. 3 times 1/6 would be 1/2 times the variable. Drop the exponent by 1. That gets you down to 2. Okay, power rule. Okay, the second one, very similar, only it's different numbers here. The exponent is a -1. The coefficient is a positive 1/2. Oops, here comes Jemanuel. So let me see if I can, oops, there's 2 people coming. And that's Jemanuel and Anita. So let me get both of them in before we go any further. Jemanuel is here, and Anita is here. Okay. Finally got a little help in the bottom part of the alphabet, Aaliyah, but the top alphabet is still growing, so recruit. Okay. Now let's see, we should be up to 9 students. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it. Okay. So I'm going to get this out of the way again. And let's go back to where we were. For those who just came in, Anita and Jemanuel, we're in Chapter 7, Applications of Integration, Section 7.4, Arc Length and Surfaces of Revolution. We're on the arc length part right now. We're on page 476, top of the page, example 2, which I have written down the first part, the given, and I rewrote the let me put this up here. I rewrote this to be, and that's a 1 right there, for those who didn't come in time to hear me correct that. Okay, I rewrote this function to be like this so it'd be easier to take a derivative. That's what we're doing now, the derivative of this. We've already done the first part. Derivative of the second part, exponent times coefficient, that would be a negative 1/2. And then your variable, drop it by 1, that goes to the -2. Okay? Now, for what's coming next, I'm going to go back and put this back in a form sort of like the original form was. Okay? And that's going to be this. Okay? If I can get that equal sign to draw. Okay? I'm going to factor out the 1/2. I probably will regret it later, but I'm going to do that for right now. And that will give me an x squared minus 1 over x squared. Okay? Now, what's the next thing that your rule tells you to do? Once you've taken that derivative, what do you do with it? Square it. Okay? Now, before I square, I'm going to write this in one other form. And that will be this, 1/2. That's still there. And this is now going to be, I'm going to get the least common denominator of x squared. And that makes this denominator become a numerator become an x to the 4th. And this will be a -1. Does everybody agree with that? Okay. Next step is to square this thing. So I think I'll continue writing here since I'm on a roll here. Y prime squared, I don't know how best to write that, okay, is equal to 1/4, because when you square 1/2 it becomes 1/4. Yuck, that'll go away in a minute. Y'all probably can't see it anyway, but it took off part of my 4. Okay, 1/4 of, now I'm going to square this. The square of x to the 4th minus 1 would be x to the 4th times x to the 4th, which is x to the 8th minus 2 x to the 4th. You square the first, twice the product of the 2, square the last, plus 1. And this one will be square the denominator, x to the 4th. And here comes somebody else. Let's see if I can figure out who it is. Can anyone see that? Who is it? Oh, Kara. Okay. You just come back. Okay, so I already had you present. Good. Okay. Okay. Now, just need to close my parentheses up here. If I can find my pen again. Oops, it went too far. Get out of there. Okay. Now, we've squared that. Now, I think I want to rewrite that somewhatly too. Let me see if I really do. I think so. Okay. So, well, not yet. Not quite yet, but we'll rewrite it in a bit. What's the next thing we're going to do with that thing? we're going to add 1 to it. Now you'll have to go back. For those who just came in, we're in Chapter 7, Applications of Integration, 7.4, Arc Length and Surfaces of Revolution. We're in the arc length part now. If you flip back one page, we're on page 476, flip back one page to the definition of arc length, and you see it's the integral from a to b, in our case 1/2 to 2, of the square root of 1 plus your derivative squared. Derivative of your function squared. So what we have to do is add 1 to this. So that's what I'm going to do next. If I can find, oh, there it is, my cursor here. So we're going to do 1 plus 1/4. Now, yeah, trying to think if I really want to. I think I do. Okay, x to the 8th over x to the 4th is x squared. And that would be a minus 2 plus 1 over x to the minus 4. Okay. That's what I've got as what's going to go into the radical. Now, obviously here, we can do a little bit with this. If I can get my pen, there it is, okay, show up. Now, what I'm going to do here is rewrite that, a little bit. 1 plus x squared over 4 minus 1/2. 2 over 4 is 1/2, plus 1 or x fourth, x to the minus 4 over 4. That's a pretty ugly 4. Okay. Now that 1 plus 1 minus 1/2, if I could get my pen to move here. 1 minus 1/2 would be 1/2. So let's rewrite that way. 1/2 plus x squared over 4 plus x fourth, x to the minus 4th over 4. All right, that's the 1 plus thing. That's what goes inside the radical. I have a problem here, and I can't figure out how I botched it up. Oh, I think how I botched it up. I said x 8 divided by x to the 4th was x squared. It's not, okay? It's x to the 4th. And nobody corrected me, not a soul. So you're letting me get away with making mistakes that's going to really cost us later. I cannot get the pen to show up in the right place. There it goes. All right. This is a 4 here, not a 2. Okay. There and there and there. Those are all 4s, not 2s. So that would be, come on over, 4th, 4th, and 4th. Okay. Now, that's what's underneath the radical. Okay. Now, so I'm going to put it underneath the radical if I can get my pen to show up. There it goes. Okay. So let's take the square root of that. Now, I want to point something out to you. That looks a lot like, if I could get the pen to show up, if I hadn't done the monkeying around with it, that would look a lot like what we had to begin with. Okay, so what I'm going to do is I'm going to factor out a 1/4. Okay, now that seems like a strange thing to do, but I'm going to do it anyway. So down here I'm going to write down that thing at the end there is equal to the square root of, I'm going to factor out a 1/4 because we had that up here too. And then what do we have left? I'm going to rearrange the terms here too. That would be an x to the 4th. Now the 1/2 here, if I factor out a 1/4, that becomes a 2. Only it's going to be a plus 2 now. Okay, and then the last term is going to be a plus x to the minus 4. Okay. Now, the reason I wrote it like that is I want you to see the similarity, and it's actually right under where I want you to see it, what we have above. This was a perfect square of this thing right here. Remember, that's what we did. We squared this to get that, which we changed to be this. Okay, well, this then also should be a perfect square, but that's the perfect square of, now by the way, 1/4, the perfect square of that is 1/2. Pull that out of the radical, and then this would be, I'm going to put it under the radical for now, x squared plus 1 over x squared squared. Okay, because you see, when I squared this, I got that. So when I take a square root of this, which is just about like that, I get a plus here. That's very fortunate, okay? Because the square root of a perfect square is just be 1/2 times x squared plus, I'm going to go back and write it at x to the minus 2. Okay, now that was a lot of weasel words and manipulation there, but that's exactly what they got. Now, I meant to ask this at the very beginning. Doesn't this seem like such a bizarre function to be dealing with? X cubed over 6 plus 1 over 2x? Why would anyone even care about a function like this? Well, the reason is in order to get a function whose first derivative squared with 1 added to it is itself a perfect square, those are hard to come by. This is one that does, and we've just shown it. This is what we're integrating then. So the arc length S is equal to, and that 1/2 can come out, so let's pull it out, 1/2 the antiderivative from 1/2 to 2, those are the limits of your integration here on x, of x squared plus x to the minus 2 dx. Okay, now all that was manipulation and monkeying around with things just to get them in the form we needed them. The integration, the calculus part, is really easy. Okay, that would be your 1/2, and then what's the antiderivative of x squared? Anyone? Please tell me. X cubed over 3. Raise the exponent by 1. When you take a derivative, you lower the exponent by 1. Raise the exponent by 1 and divide by that new exponent. Okay? And then when we do the same thing here, this will actually become, oops, my internet, it said it was unstable. Were y'all still following me? It flashed on and flashed right back off. Okay? raise that next exponent by 1. That becomes an x to the minus 1 divided by minus 1, and that's what I did. I changed the plus sign to a minus sign. Okay, and then we're going to evaluate this from 1/2 to 2. Okay, all right, so that's going to be a 1/2. And when you plug a 2 in there, you get 8/3. Okay, minus, plug a 2 into that next part, you get a 1/2. Okay, minus, plug a 1/2 into the first part. 1/2 cubed is 1/8. That would be 1/24. But that's going to be a minus now. And the other part is a minus, which becomes a plus. One over 1/2, which is 2. Okay, that's all in the parentheses. Okay, so let's see what we can do to. Where is my pen? I can't find it. Did anyone see my pen? Oh, it's way up. There it is. I see it now. Okay. All right. So that would be a 1/2 times. Let's add these things together. 8/3. Well, let's see. Let's get it to 24ths. That would be 64 24ths. Right? Because 3 will go into 24. 8 times 8 times 8 is that. Minus 12 24ths. That's what 1/2 is. Minus 1 24th. That was already there. Plus 48 24ths. Which is 2. Okay. Now that will be, let's add those two together, 112 minus 13, I think is 99, isn't it? 99 24ths, and you got the 1/2 in front. Well, I know 3 will go into 24 8 times, and 3 will go into 99 33 times. So that's going to be 33 over 16. Just a little bit more than 2. Okay, and that's supposed to be an equal sign there. The bottom part of the equal sign did not show up today. Okay, let's see if that's what they got. Oh my goodness, looky there. They did. 33/16. All right. To me, arc lengths are not a lot of fun. You have a lot of steps, and some of those steps leads to some really bizarre expressions. And I can, oh, and here comes Daniel. Okay, well, I can't get him in until that disappears. Okay, there's Daniel coming in. Or he's either Jonathan or Daniel. I can't figure out which one. I see him signed both ways, or it shows up both ways. Okay, in case you just, yeah, Daniel, I see you got your microphone and all. We're just finished example 2 on page 476 in chapter 7, application of integration, 7.4, arc length and surfaces of revolution. We're just doing arc length. This is our second example of arc length, and it was a doozy because it was a really bizarre function. Why such a bizarre function? you have to have functions whose derivatives squared with 1 added to it also is a perfect square, okay? And that's what we had, and it was bizarre but true. All right, and we got that answer, so you can go back and follow us all the way through or follow it in the book. Now, these are not on the slide set, that's why I'm doing them here. Excuse me, any questions on that one before we move to example 3? One thing I meant to do when I was coming upstairs after lunch, I have to eat lunch awfully early on Mondays and Wednesdays, at least this Wednesday. I meant to bring soft drink up because I've got weird stuff going on in my throat. Sometimes I can hardly talk. Okay, so but I forgot to bring it up. I do have some water here, but it's not as bubbly. So no questions on example 2. Move on to example 3, bottom part of page 476. All right. Let me see if I can write it from here so I don't have to hold the book. Find the arc length of, okay. Nope. I keep bumping this. Oh, wait. Heading the wrong direction. Okay. Let me, uh-oh, my screen sharing paused. I must have hit something. Oh, I know what happened. It's supposed to be on the whiteboard, and somehow it went back to PowerPoint. Okay, here we go. Don't know how that happened. This Wacom will hit the computer key and do something to it, and I can't ever figure out exactly how it did it. So here is find the arc length of the graph of y minus 1 cubed, another weird looking function, y minus 1 cubed is equal to x squared. Okay, on the interval 0 to 8, and it says is shown in figure 740. Let me show you figure 740. Okay, this is one side it's a cubic function, the other side it's a squared function. There is the graph of this from 0 to 8 on x. Okay, now written this way, that would sort of suggest to you, let's do our dx's. But frankly, that looks like the hard way to go to me. Seems like a far better suggestion would be write this as x's in terms as a function of y. Okay, and that's exactly what they do, because otherwise you wind up with cube roots, which are not particularly fun to play with. This way, at least it's a square root that we're a bit more used to. So let's rewrite this, if I can get my, okay, now it's drawing things where I don't want it to draw things. I hadn't even gotten close to the screen yet, and yet it's threw in a couple of things. Okay, now if we change this, okay, take the square root of both sides, and that would give you x is equal to y minus 1 to the 3/2. Now that's at least a fairly reasonable looking situation, but what we've got to do is figure out what the limits are for your y now. So what is that? What are the limits for y? Okay, Now, let's start with x equals 0. In the upper equation there, when x equals 0, it seems like to me fairly obviously y has to be 1. Would you agree? So we'll start there. Y going from 1 to, and when x is equal to 8, x squared would be 64. The cube root of 64 is 4, because 4 squared is 16 and cubed is, okay, so that'd be 4. So what's inside there has to be 4, so y must be 5. Okay, so y is going from 1 to 5. Now let's go back and look at our picture there, and sure enough, the y values are going from 1 to 5. I don't know if you picked that up when I held it up. I couldn't hold it too long because it's too heavy, but there's the graph, and you see when x is going from, where is, there it is, when x is going from 0 to 8, y is going from 1 to 5. Nice, smooth, continuous function. So yeah, we can do this. All right. So with that in mind, we need to do what? Take x prime. This represents dx dy now, because y is now your independent variable, x is the dependent variable. And what would that be? You can do a power rule right here, can't you? 3/2 times y minus 1 to the, subtract 1 from that, that would give you 1/2, and derivative of the inside is just 1. Okay, so that's what you get. Now we have to square that. Remember, that's the next step, squaring it. So I'm just going to call that x prime, because I don't want to write it all, squared will now be 9/4. You square the outside. Now, when you square something to the 1/2, it just becomes the function, right? So that becomes y minus 1. Okay, now let's expand that a little bit. 9/4 y minus 9/4. The reason I do that is because the next step is to add 1 to that squared entity. And adding 1 to that squared entity would just be adding a 1 to it. Now this equal sign is no longer valid, okay, because I'm adding 1 to it, which is 1, of course, is 4/4. Okay, so this is going to then be 9/4 y minus 5/4. There's your wait a minute. Yeah, that's right. Okay, that is your what's underneath the radical. Okay, now unfortunately it's not too pretty. Where's my pen? There it is. Okay, let's factor out a 1/4, and that would give you 9y minus 5. Okay, now what are we going to do with that? We need to take a square root of it. Okay, because, okay, we started with taking a derivative, we took that. Then we squared that derivative, we got that. Then we added 1 to that square of the derivative, we got that, and now we're taking a square root of it. So the square root of this, and this, by the way, if I can get my pen to move, there it is. This will produce the, when I take the square root of this, I'm going to get a 1/2. So I'm going to pull that on the outside. And we'll have the integral going from 1 to 5 on y. 9y minus 5 to the 1/2 power dy. Now this is looking rather suspicious. Nope, that's exactly what they got. Okay. Now, how do we do the antiderivative of that? Okay. Now, if you wanted to, you could go back and do your u thing. Let u equal 9y minus 5. Du would then be 9 dy. And I think that may be the best way to do it. Let u, but this time it's not a function of x, it's a function of y, equal 9y minus 5. Then du is equal to 9 dy. Well, up here you have just a dy, so let's divide both sides over here by 9. Okay. Boy, this is like pulling teeth here. So what is your new integral? The new integral is, and we haven't made our change of variables yet, so we'll do that in a minute. The 1/2 is still out there, but I'm going to combine with that 1/2 1/9, because the du part is going to have a 1/9 in it. So that'll be 1/18. 2 times 9 is 18. The integral. And let's go and get our new limits. When y is equal to 1, this would be 9 minus 5. U would be 4. Does everybody see that? When y is equal to 1, the lower limit here would be 9 times 1, which would be 9 minus 5 is 4. U would be 4. At the upper limit there, when y is equal to 5, 9 times 5 is 45, minus 5 would be 40. So the upper limit, yuck, why does it do that? Is 40. Okay. And then this would be u to the 1/2 du. Okay. Yuck. That'll go away in a minute. You probably can't even see it anyway. And now this becomes a du here. If I can get the pen to cooperate. Du. That's what we got here when we did the dy was 1/9 du. We pulled out the 1/9. All right, now the integral of that, we know this is 1/18 times antiderivative of u to the 1/2 is u to the 3/2. You have to increase that by 1. Okay, times 2/3. Okay, and that's evaluated from u is equal to 4 to 40. Goodness gracious, I may have to go down and get that soft drink. I'm losing my voice pretty badly. Let's go on and pull the 2/3 out of that too, because that's not going to change anything. So 2 will go into 18 9 times, and that leaves us as a 1/27. And then we'll evaluate this from there to there. Okay. So we got, come on. Okay, here it goes. That's this is rather awkward. 40 to the 2/3, 3/2 power. Okay, minus 4 to the 3/2 power. Okay. Now, let's pause for a moment and think about what those quantities are. Let's first take the square root of 40. The square root of 40 is 4 times 10. So square root of 4 is 2. So that's 2 times root 10. So I'm going to come over here and write my answer. 1 over 27 times what does? Just say square root of 40 is 2 root 10, and then we've got to cube that. So that will be 8, that's 2 cubed, times the square root of 10 cubed. Well, the square root of 10 squared is 10, so we'll make this 80 here, times root 2. Okay, believe that's right. Minus, now the next part is pretty easy. Square root of 4 is 2, and 2 cubed is 8. So that's minus 8. All right. That is a weird answer. Now, they didn't even take it that far. They left it as 1 over 27 times 40 to the 3 halves, exactly like I have it right here. They left it in this form right here. We just carried it one more step. They rounded then. And if you got your calculator, you can pull it out. Let's just make sure my answer gives the same result as theirs. Now, I'm on a cell phone, which doesn't have as easy to manage calculator as, say, a graphing calculator or a scientific calculator. Okay, I can't even get mine to go to the mode. There we go, it finally did. All right, 40 okay, and I use a y to the x, or x to the y key, so I'll press that key, and then my exponent is 1.5. Okay, I'm just going to put an equal sign there. That gave me something on the order of 253, but don't mess with that yet. Minus, and we had already done that, that's minus 8, okay, equal, and then divide that by 27. And I got 9.073 just like they did. So yes, these answers are equivalent. Okay, mine was just written in a different form. Okay, so we can write down that approximate solution is, that is the exact solution. The approximate solution would be 9.073. Okay, and looking at that graph, you see you're going, in the x you're going from 0 to 8, and in y you're going from 1 to 5, so it's not at all surprising. It would be a little bit greater than 8, but not that much greater. Okay. All right. Can't believe we've only been at it an hour, okay, and not even that. Okay. At some point I'll have to take a break. I can just feel it coming. Let's move on to example 4. Okay, and this is also finding an arc length. So it's all right for me to clear the drawing here. Okay, and on this one, even though they don't show it in the slideshow, they do show it at larsoncalculus.com. So you can go to that website and see an interactive version of this type of an example. So here it says, find the arc length of the graph of y is equal to Where, oh, where are you tonight? Up. Okay, I don't know why it does that, but it does. It took me away from the whiteboard and cleared the screen. Okay, so here's our problem. Oh, there's my pen. Finally came back. The arc length of the graph of this, y is equal to the log of cosine x. Now, does anyone want to guess what a potential limit might be? It's going to be a parentheses, and I don't know if you know why it's going to be a parentheses, but it is, okay? Because picture cosine x. Okay, I'll take that back. It doesn't have to be a parentheses, okay? But to get the longest arc length that you are going to get with this formula, cosine x is positive from negative pi halves to positive pi halves. So if you're stretching that to the limit, you cannot have a zero in there. And cosine of negative pi halves and positive pi halves are zero at both ends. So if you were going to do the maximum arc length there, you would have to go from open parentheses negative pi halves to positive pi halves. But let's see what their problem calls for. They say from x equal to 4 to pi fourths. That would be perfectly fine. And you can put it in parentheses or brackets. They put it in brackets, so I'll go back and change it to a bracket as well. Okay? Come on, where are you, pen? Okay, for some reason the pen, well, I know why the pen has quit moving. I was doing it on my touchpad, not on the screen. Okay, now, come on over here. There we go. Okay. Okay. So I'll change that to a bracket. And this is going from 0 to pi fourths. And cosine is positive everywhere in that interval. Okay? Cosine cannot be 0, it cannot be negative, otherwise you couldn't take a log of it. But from 0 to pi fourths, cosine is always positive. Okay? Now, here, by the way, is sort of what I was talking about, is the graph of this thing. Okay? There it is. Okay? Now, you can see that this is all below the x-axis. That doesn't matter. We're doing arc length. Arc length can be anywhere it wants to be. Okay? We may have some weird thing come up with it, but that's okay. We can handle weird stuff. Okay? So, what's our first step? Take a derivative. Y prime is equal to, and what would that be? Here the calculus part is a little interesting. What would that be? Anybody? What's the derivative of a natural log? 1 over the argument. So 1 over cosine x, okay, times the derivative of cosine x. The derivative of cosine x is minus sine x. Okay, so that's your derivative. Okay, we're not going to stay there. We're going to square it. So that derivative squared is, and by the way, that is sine over cosine is tangent. So that's a negative tangent. So this would be tangent squared, because it doesn't matter about the negative part. This is going to be tangent squared. X. Okay? Now, what's the next thing we're going to do to it? Is add a 1 to it. Okay? And at this point, the equal signs don't make any sense. And then what are we going to do? And by the way, before we do whatever the next step is, which I think you know, what is tangent squared plus 1? Please tell me you know. I have to talk with your trig teacher. That's the Pythagorean identity, which is exactly secant squared. Okay? Because 1 plus tangent squared is secant squared. And what's the next thing we do to it? Take a square root. So when we take the square root of this, which now the equal signs don't make any sense anymore, that's equal to secant x. So what we have here is the integral s is equal to the integral from 0 to pi fourths. Goodness, I can't draw the line well. Okay, of secant x dx. Okay, now here's where we run into a little bit of an issue. Okay, do you remember what the antiderivative of secant x is? You may or may not, but here's what I recommend, especially if you don't remember what that is. Oh, here's Joy. I hope she hasn't been waiting long. I can't find my cursor. Where is it? There it is. Okay, let's set Joy in. Undo the blue line. Aaliyah, you're probably finally having some help down there. Okay, there we go. What I do for something like that, rather than trust my memory, I go to a table. And in the front of your book, you have a table of integrals. You have the top inside cover, and most calculus books have this, is first at the top of the page a table of derivatives and then a table of integrals. Okay, and if you go down into the trig functions there, you'll see number 12, the antiderivative of secant u du, which is exactly what we've got, is the log, and it's exactly what they got too, the log of natural log of the absolute value of secant x plus tangent x. That is so ugly. Okay, now we're evaluating that from, come on pen, there we go, from 0 to pi fourths. Okay, now you don't need to worry about the absolute value sign. Secant is positive from 0 to pi fourths, tangent is positive from 0 to pi fourths, so you're okay. But now you might, no, it'd still be okay. Okay. I was going to say that may have been a reason they only went from 0, because tangent goes negative in the left of 0, but that's okay. Secant's still positive from negative pi halves to pi halves. So you would have been okay, but we're just doing this portion here. So let's take what we've got and plug it in. This will be the log of, I'm going to change it to parentheses now, secant of pi fourths. Does anyone remember what that is? Okay. Secant is 1 over cosine. Okay. And cosine x at pi fourths is 1 over the square root of 2 over 2, which is 1 over root 2, so this would be root 2. Okay, so secant of pi fourths is root 2. Okay, now tangent is tangent of pi fourths is 1, so that's plus 1. Okay, minus the log of, I'm going to again use open parentheses here because I know it's going to be positive, secant of 0 is 1, but tangent of 0 is 0. Well, anyone remember what the log of 1 was? 0. Okay, so our answer is just simply log of root 2 plus 1. The natural log of root 2 plus 1. And you can figure out what that is. And they do it on a calculator too, I assume, so I will do the same thing. Let me get my phone back turned on again. Calculator again, calculator again, sideways again, there it goes. Clear that. Now, why is this happening? I'm not touching anything on the screen and Zoom is just screwed up. Can anyone hear me? It looks like we got disconnected from Zoom. Can anyone still hear me? Okay. I have no idea why that happened. We do have some rain falling, as it does with us every day, so there may be a storm somewhere that broke the connection. But I'm outside Zoom now. It's trying to reconnect, so I'm not going to do much more until it comes back on. I don't think you can hear me, but I'm talking anyway. I think what I'll do is end this and pick it up again. Okay, I'm reconnecting. I don't know what the problem is. It could, oh, wait, I see what the problem is. I don't have any internet service. Yuck. Here's what I'll do then. I'll try a different one. Wow, that's my best choice. Let me try this one and see if that works. All right, folks. Okay, it looks like we've got internet. So now let me change this and start again. Okay, folks, I'm connecting again. This is all getting recorded. I should have probably paused the recorder too because nothing's happening. I think I'll do that now, but not all. Where we were was the log of, this is the answer to example 4 on page 477, and that answer was the log of, natural log of the square root of 2 plus 1. Okay, that's what we got. They wrote it slightly differently. Let's see if we get the same answer. So I'm going to type in my 2, take a square root of that, add 1 to it, and then take a natural log of that. And we got 0.881, exactly like they did. Okay, so yeah, same answer. Okay, clear the screen and shut that down. Okay, that was example 4. That's all we get left on the board here. Any questions on example 4? All right. Now, just because I know the next one's going to take a lot of space, I'm going to go and clear this out of the way. Now, let's move to the next example. Example 5. An electric cable is hung between 2 towers that are 200 feet apart, as shown in the figure here. The cable takes the shape of a catenary. I don't know if you've run into that before. Here's its equation. Y is equal to, now y is the vertical part, is equal to 75 times e to the x over 150 plus e to the minus x over 150. And then they give it to you in hyperbolic cosine, which is a pain in the neck, and there's no reason to really do it. Okay? Because we're going to use it in the exponential form. Okay? So that's where we begin, is what our y is. So let me see if I can find, there it is. Y is equal to 75. Now, they don't tell you where the 75 comes from, but we'll just take their word for it. 75 times, I'll tell you exactly where it comes from. The hyperbolic cosine is 1/2 of this expression we're going to have here, and 1/2 of 150 is 75. So that's where it came from. E to the x over 150 plus e to the minus x over 150. Leave it in exponential form. The hyperbolic cosine does nothing for you. Okay, find the arc length of the cable between the 2 towers. Now, what they do here is a smart move, a clever move. I'm really worried about this pen because those are easily breakable and very expensive. Okay, what they do in their figure here is put the y-axis exactly halfway between the 2 towers. Okay, so we would be calculating from negative 75 to plus 75, but let's just do from 0 to plus 75 and double the answer. Okay, now okay, so the first thing we're going to do, as always with arc length, is take a derivative. So the y prime here is equal to, keep the 75 out front, it will change later, and then here the derivative of e to the x over 150 is e to the x over 150. Okay, times 1 over 150. Same thing's going to be over here for that one. So basically you can pull the 1 over 150 out, okay, and not have it hanging around in here. Okay, then this one, the derivative of this, is going to be the same, except it's going to be a minus e to the minus x over 150. Okay. Now, this becomes 1/2. Okay. Now, we've got to square that. Okay. When we square that, y prime squared is equal to 1/4. 1/2 squared is 1/4. And then you would have square the first one, which would be e to the x over 75, right? When you square a number raised to a power, you double the exponent. So we multiplied it by 2. And when then you have twice the product of the 2, so that's going to be a minus 2, okay? Because e to the x over 150 times e to the x over 1 over x of the 150 is going to be 1, okay? And then we have a plus, the square of the last is e to the minus x over 75. Okay, now I'm doing a lot by talking because it's hard enough to write on this thing as it is and not to put every step. If I'm confusing you, if you don't understand where each of these steps comes from, please ask. I'll go on and fill in the gaps. Okay, any questions? Is everybody in agreement now? Okay, now what are we going to do with that? We're going to add 1 to it. Now, before I add the 1, I'm going to do very similar to a couple problems ago. This will be 1/4 e to the x over 75. That will not write, okay? Minus 1/2. 1/4 times -2 is minus 1/2. Plus 1/4 e to the minus x over 75. Pretty ugly x. And a pretty ugly 5. Okay. I don't need the parentheses there. I don't know why I wrote it. Okay. Now, we're going to add 1 to this. So adding 1 to that basically is going to go from minus 1/2 to plus 1/2. There I added the 1. Okay, and then we're going to take a square root of this. Now, here, just like what happened before, when you squared this thing up here, you got this, okay, which was, remember, a minus 1/2 in here, okay? Well, now we've got the same thing except plus 1/2, so that indicates that you're squaring the same thing but with a plus sign. And that's exactly what you're doing. So this is the perfect square of, I'm going to pull out the 1/4, just like we did before. And the square root of 1/4 is 1/2. Okay. And then the perfect square that was in here was e to the x over 150. Yeah. Plus e to the minus x over 150. Okay, that's really ugly. I can't believe how poorly the pen's writing. Okay, so that's what we've got. I will put a parentheses after that. So there we've taken the derivative, squared it, added 1 to it, then took the square root of that, and this is what we get. That's what we then integrate. So let's do the integral here. I'll put the limits here. This will be your s is equal to, now they are saying from minus 100 to 100. Okay, what I'm going to do is take that, multiply it by 2, if I can find my pen here. Multiplying 1/2 by 2, it's just going to make it a 1. And we're just going to take it from 0 to 100. Okay, those are your x values there. And this, of course, is dx. I forgot to write that down. Okay, now we've got to take that derivative. And that's not really awfully bad. Antiderivative, I said derivative, antiderivative of that would be e to the x over 150. Okay, now if we were taking a derivative, we would multiply by 1 over 150. We're not taking the derivative, we're doing the antiderivative. So that's multiplying by 150. If I can find my pen, where did it go? There it is. Okay, so that's going to be a 150 here. Okay, and it'll be on that one, and it'll also be on this one. Only that's going to give us a minus here, e to the minus x over 150. And we're going to evaluate that from 0 to 100. I'm not going to mess with the slashes. They're not drawing anyway. Okay. Wow. So this gives us 150 times e to the 2/3 minus e to the minus 2/3. Okay, and then we'll do a minus 0 when you plug in a 0. Okay, and I shouldn't have closed that one out so soon, so let me, where are you tonight? There you are. Okay, let's not close that out yet. Okay, when you subtract e to the 0, e to the 0 is 1. Okay, so you subtract e, you subtract 1, then you have a minus 1 again. So those do add to 0. So now I'll close it out. Okay, and that gives us 150 times that difference. So if I write it down again, let's see what we get in the book. I get 150 times e to the 2/3 minus e to the minus 2/3. That's exactly right. And we're not going to do that. Let's see what that gives us. All right, again, turn on the calculator. And it's 1 o'clock. Okay. There we go. All right, e to the 2/3. So in my calculator, I have to do 2 divided by 3, my phone, equal, and then do the exponential key, e to the x. Okay, minus 2 divided by 3, 2 divided by, I botched this up. I'm going to have to start over. Okay, sorry about that. 2 divided by 3, my finger hit the wrong key, equal, and take the exponential of that, you get 1.945, not 95, something like that, minus 2 divided by 3, that time I hit it right, equal, change the sign of that and do an e to that and get an equal there, and multiply that by 150. And it didn't come anywhere close. I did something wrong. Let me try that one more time. Okay. E to the 2/3. Okay. 2 divided by 3. Nope, I messed it up again. 2 divided by 3 equal, e to the that is 1.94 blah blah blah, minus, okay, 2 divided by did it again, 3. Oh, I know what I'm doing wrong. I need to put some parentheses in here. Okay, let me start again. 2 divided by 3 equal e to that. Got that part. Minus, now I'm going to open up parentheses. Okay? 2 divided by 3 close parentheses, e to that, and then do an equal. I forgot to change signs. This is so frustrating. Let's just say the answer is right, but I'm going to try it one more time. 2 divided by 3. It's so much easier on a graphing calculator or any scientific calculator than on the telephone. It's equal to that, e to the that, minus, open parentheses, 2 divided by 3, close parentheses, change the sign of that, e to that, equal. That time I got 1.43, multiply that by 150. And we get something in excess of 215, which is what the book got to. The arithmetic is the hard part. The calculus is the easy part. Okay, so that came out something on the order of, where's my pen? There it is. On the order of 215. I believe that was in feet if my memory's right. Yeah, 215 feet. All right, so that was example 5. Now finally we're ready for, okay, we're down to, wait, Houston's here. Good deal. All right. Good to have you here, Houston. We're right now on, just got to Chapter 7, Applications of Integration, Section 7.4, Arc Length and Surfaces of Revolution. We've already done the arc length part. Now we're starting to do the surface of revolution. Okay? So that's going to go back to 7.4 and from current slide. And that's where we left off before. All right, area of the surface of revolution. Okay, now it's 105. We've been going at it since 11:30, so it's 12:30. An hour and a half. And we're just about midway. Is it okay to take a quick break? I need a bladder break. I know we've had a break that I didn't get to go anywhere because I was trying to get our internet back. So Houston, you just got here and we're going to take a break because you're here. Never mind. So hold on. I'm going to pause the recording again. My internet went out, Houston, is what I was talking about before. So let's pause this and have a quick break. I hope to be back in less than 5 minutes. Okay? Hold on. Okay. I see, Houston, your light's on, but your microphone's not. Can you hear me? Anybody? Yay or nay? Yes. Okay, good. All right, want to make sure. Oops. Okay. Okay. Let me get my microphone attached a little bit better. Headset attached. All right, so where we're starting now in chapter 7.4 is area of a surface of revolution. Now this is very similar to calculating a volume given a segment, okay? Given an area under a graph, we did rotating discs, rotating washers, or rotating shells, okay? From an area, we are able to get a volume. Now what we're doing is having a line length, a curve, arc length, rotating that around an axis, and that's going to give us a surface. So it kind of makes sense, and this is what we'll be proceeding with here. And for some reason, it won't advance until I click on it. Okay, now, here's the definition of a surface of revolution. When the graph of a continuous function, the graph, that is a curve, is revolved around a line, the resulting surface is called the surface of revolution around that line. The area of the surface of revolution is derived from the formula for the lateral surface area of the frustum, I think that's misspelled, isn't it? No, frustum, I thought it was, I had an R in it. Frustum of a right circular cone, okay? And of course you know what those are. That's one of your favorite objects of all time, okay? So here's, consider a line segment, just a line segment, L, okay? Where L is the length of that line segment. R1 is the inner radius there. Let me see if this will even show up. Yeah. R1 is the inner radius, okay? And R2 is the outer, the larger radius, okay? Now, the line is slanted in that direction. That's why R1 is smaller than R2. You're revolving that line around the axis of revolution that goes down, that looks like it might be the x-axis, whatever. You're making a lampshade, right? Well, of course, that's what we were trying to make, okay? When the line segment is revolved around the axis of revolution, it forms the frustum of a right circular cone, and that area is 2 pi times r. That's not the R1 or R2 that we had before, times L, okay? Now, that's the lateral surface area of a frustum, where the R there is exactly half the average between the R here, R1, and R2. So basically we add R1 plus R2, divide by 2, and that gives you R right in the middle, okay? Okay, so you're assuming that is you have a length and you're going around a circumference, okay, of that radius R, and that gives you your surface, okay? A length times another length, radius, gives you an area, okay? So your R is your average between the two endpoints. Now, consider the function f, which has a continuous derivative on the interval a to b. Continuous derivative meaning there's no corners, no cusps, no angles, smooth curve, okay? So consider a function as a continuous derivative on that interval a to b. The graph of f is revolved around the x-axis to form a surface of revolution, okay? Now we've got something, here is your function here, okay? And you're revolving this around the axis of revolution here, okay? And that gives you a nice, looks like sort of a chalice or something like that turned on its side, okay? Now, what we're doing is taking a little delta x here between x sub I minus 1 and x sub I. That's a big old delta x here. Let's imagine it much smaller, like right there, okay? And then this segment here is very close to being a straight line. Even this big old segment here was pretty close to being a straight line. If you had done that big a segment here, that would have been nowhere close to the same length, okay? So take a small enough one and it's going to be close to being a straight line, and that's what you're revolving around the axis of revolution, okay? Now, if your del or delta or whatever you want to call that, delta, is your partition of A to B with subintervals of width delta x of I, this is all stuff we've done over and over again, then the line segment whose length delta L sub I is the square root of x squared plus delta x squared I, x sub I squared plus delta y sub I squared, okay? Basically just like we did when we were doing arc length. This delta L is just like an arc length. Let R be the average radius of the frustum, R sub I. By the intermediate value theorem, the point D sub I exists in the I subinterval such that R sub I is exactly equal to f of D sub I. Okay, lots of blah, blah, blah. The lateral surface area, delta S sub I then, of the frustum is then 2 pi times that radius that we got, okay? That's a circumference. 2 pi r is a circumference times the length of that segment that's being circumfered around there, okay? And that gives you that. Well, the delta L sub I is just like your arc length, okay, which is the square root of 1 plus what's going to wind up being y prime squared, okay? So the only thing you're doing, you've got this was your arc length right there, okay? Sorry, that popped up in the way. I don't know if you can see it or not, okay? And you multiply that by 2 pi times your function, which is how high above the x-axis you are. That was your y sub I in this illustration here. Your f sub I was, where is it? There it is. Your f sub I was how far above here. You're going around the x-axis, so that gives you f sub I 2 pi times that length. Okay. Now, by the mean value theorem, the number c sub I exists on the interval x sub I minus 1 to x sub I such that f prime of c sub I is exactly your derivative. Okay, your f prime is the change of f sub I over the change of x sub I, and that's your rise over run, dyi over dxi. So the delta s sub I is 2 pi times the function at some value there, d sub I, okay, on that ith interval, times what looks just like your arc length function, and that's exactly what it is. The total surface area is approximated by 2 pi times the summation of f sub x sub I times the thing that looks like your arc length. And then as you take the limit of the right hand side of that as your del, the norm of del, norm of your partition is approaching 0, that means your n is going to infinity, then the total surface area is 2 pi, that's out front, times this, that's your radius, 2 pi r, times your length, there's your arc length, and go up from A to B. It's just pretty simple and straightforward like that. 2 pi your radius times your arc length that's being circled like that. In a similar manner, the graph, if you're revolving around the y-axis, then you get your x is some function of y, and take the derivative of that, square it, add 1 to it, take the square root of that, and then This time, though, going around like this, it's not f sub x, but it's x, because that is what you're going around there. Now, notice what they did here. Tricky, huh? They didn't change from a dx to a dy. They just changed from an f of x to an x down here, because up here it's the y value is your radius. Over here is the x value is your radius. So you can leave your function in that same f prime of x squared, because guess what? That's the same measured this way as it is measured that way. It's the same, okay? So that's the difference here. If you're revolving around the y-axis, all you change is your radius of rotation, which is now x, not f of x. When it was around the x-axis, that radius was your y value, which is f of x. Now it's the x value, which is just x, and leave everything else the same. So you don't need to change to functions of y. In those two formulas for s, you can regard the products 2 pi f of x and 2 pi x as circumferences of circles traced around the point xy on the graph of f as it's revolved around the x-axis when you use f of x as your the y is your radius, and around the y-axis when you just use x as your radius. In one case, the radius is r is equal to f of x, in the other case is r is equal to x. Now, what they haven't said, and it's all doable, is if you had a line parallel to the x-axis, above, below, wherever it is, then you just have to calculate your radius from that line to the curve, okay? If you have are revolving around a line that's parallel to the y-axis, you just do the calculation of that line, the distance from that line to the curve, okay? And it still works the same. Just adds a little more complexity, but it's not too bad. All right. Now, they may not even be going to do that, but you could if you needed to. So let's have, I hope that's going to stay there now. Let y equal f of x have a continuous derivative on the interval a to b. Okay? That means a nice, smooth function. Okay? The area S of the surface of revolution formed by revolving the graph of f about the horizontal or the vertical axis is S is equal to, now this is capital S. Arc length was little s, surface area is capital S. 2 pi, they both have 2 pi's. And why are they going back and changing this? I don't know. I do not know. All right. It baffles me. Okay, I think I get what they're saying. Okay. The surface of revolution is formed by revolving the graph of f about a horizontal or vertical axis. It's no longer the x and the y-axis. That's what the difference is here. So your r of x is now your radius from that new axis. Now it may be that that's just the x-axis, and then that would be your f of x, okay? But if it's anything other than the x-axis, then you have some r of x, okay? Where r of x is the distance up between the graph and the axis of revolution. Doesn't matter where it is. Now that's if it's a horizontal, okay? If you change that x to a g of y on the interval c to d, then the surface area would be this, and now you're going around the y-axis, or around an axis parallel to the y-axis, a vertical axis. Let's put it that way. That's an easier way to say it, around the vertical axis. So now it's beginning to look more like your arc length things when you have functions of x or y. Okay. So let's do example 6. This is on top of page 480. Okay. Find the area of the surface formed by revolving the graph of f of x is equal to x cubed on the interval from 0 to 1. Okay, that's pretty much that. About the x-axis is shown here. Okay, so that's pretty much just a simple form like we did before. Okay, so let me go to screen share, whiteboard. All right, let's clear that one out of the way. Y'all all right with clearing it? Okay. Now, did we do this one since? No, that was earlier. It seems like that before the the thing went off, so I'm sort of surprised it's still there, but whatever. I'm not going to go back and try to recreate it. Okay, so here's what we've got. Find the area. Here's your graph. F of x is equal to x cubed. Okay. Find the area of the surface formed by revolving that graph on the interval from 0 to 1. Oops. It really doesn't matter whether you put parentheses or brackets. It doesn't matter. About the x-axis. Okay. Now, I don't want to have to draw it, so I'm going to show it to you. Here's the figure. There's your y is equal to x cubed, and revolving that around the x-axis. So it's a very sort of a coolie hat, you might say, on the side. Okay. So what would be your approach here? A surface area of revolution is always 2 pi times the radius of revolution. Well, since it's going around the x-axis, that's 2 pi times your f, your y value. So that would then be your inside the integral, and this is going from 0 to 1, you're going to have an x cubed, because that's your f value. Okay? Then the rest of your function is the square root of, okay, basically your arc length function, which is 1 plus f prime of x squared, and then that's multiplied by your dx. Okay, so one of the first things we've got to do is find out what f prime is. What is f prime of x? Pretty easy. 3x squared. Okay, so let's go back, plug that in. 2 pi times the integral from 0 to 1, x cubed times the square root of 1 plus, and 3x squared would be 9x to the 4th, right? Times dx. All right. Now, this works out far nicer. Whoops, here's James is coming in. So let me get my thing to work here. James Mullins is here. And James is right below the blue line. There you are. Okay, the bottom part of the alphabet is catching up with the top here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Almost. Okay. So we should have, yep, 12 people. Well, actually, we've lost somebody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, we've lost somebody. In fact, we've lost two somebodies, because we're down to 11, but I had 13 here. Now, since we have started losing some people, I'm going to take a time out here. Unfortunately, we did this before. James, you just got here, and I'm taking a time out. And here's the reason. Here's that rarely important announcement that I need to make. And it's somewhat of a little bit of a confusing announcement, but let me get it in here. This came from the Vice President of the College for Instructional Services. And he said we're supposed to call roll from our official class rolls, which means only from the paid students. Now, folks, this is what we did back when we were in a class. Okay? I'm not doing that now. I mean, I don't come in and then call the roll. As you come to the classroom, I mark you present. Okay? And I mark you in my grade book, which has all the names in it. Okay? There's no indication of whether someone's paid or not. That's what the official class rolls do. Okay? Now, here's what it says then after that. If any students in your class are not on the official roll, which means they have not completed their payments somehow, those students need to contact the business office, and I have a phone number here. I'll let you see that phone number. There's the business office phone, 205-929-6334, or the Financial Services Office, and that number is 205-929-3422. Okay? If you're waiting on a Pell Grant or something like that, or some type of assistance, a scholarship, or anything else that the Financial Services Office would be involved with, that's the number you call. If you're paying out of pocket, cash, credit card, whatever, and you haven't completed the payment, get in touch with the business office. Basically, you need to be talking with the cashier or someone the cashier works for, somewhere like that. Now, here's what he says. You should not allow the student to participate in class after today, Wednesday the 28th, the 8th. And it says you can obtain, it tells us where we can get the official rolls. Well, guess what? Okay, this is how we're operating now. I put the message on Blackboard about the Zoom, and then you come into the class. Now, I guess I could not let you into the class, but that doesn't seem very humane, to say the least. Here's how, okay, if the administration wanted to enforce this, all they would have to do is remove the names of unpaid students from Blackboard. If they did that, you wouldn't be able to get your invite, and you wouldn't be able to attend class. Okay? If they wanted to do it, why won't they do it that way? It's so simple. But no, he wants us to calling rolls from the official. It's just sort of ludicrous the way they do it. Now, let me back off and make another statement here. Okay? If you are going to complete payment, if you are going to pay for the course, I want you in the class. I don't want you missing class and then you're having to make it up. I want you in the class. Now, if you're not going to complete payment, I don't care if you're here or not. I mean, I like having you here, but guess what? You could be here for every class. You could turn in every homework. You could take every test. You could make an A on everything. If you don't pay for the class, you're not getting a grade. I can't give you a grade because you're not on the official roll. So that, to me, would be the simplest way of saying this, folks. If you don't complete your payment, you're not going to get a grade. Period. That's it. Okay? I don't care if you're here or not here. You're not getting a grade if you don't complete payment. Now, what they're kind of saying is they want you to complete payment this week. Now, somebody from the class had emailed me and asked me when the last day to complete payment was, and you never know until I got this email. So after I got the email, I emailed her and said, here's what they say. And then she's not here today, so I don't know. I hope that didn't discourage her from coming. But I tried to tell her, if you're going to complete payment, please get it done this week. Get it done now, as soon as possible, and don't miss any classes. If you're not going to, I don't care what you do. You can continue coming or not, but guess what? You're not going to get a grade. And they may not accept payments after this week or sometime soon. Knowing them, they'll take your money. So I'm not as worried about that. But you can't bank on it. If you're too late in getting the payment done, I don't know. I guess they'll turn you away. But they're trying to get everyone to pay this week. Please do so. Now, I had marks by people's names earlier who had not paid, and at least 1, 2, 3, 4 of those people, there were 5, the one that I had the email from is not here. 4 of those 5 are here today. I think you probably know who you are. If you have completed payment since I marked this, which was weeks ago, then you're fine. Okay. If you have not, though, please do it this week if possible, because my guess is after sending these emails, they're going to remove people who have not paid from Blackboard and from other places. And if you're removed from there, you're not going to get an invite. And I won't know it until I go to put roll in the next time after the next class, and then I'll see your name's been removed. So I have no control over that. They control who's in Blackboard. And they would make it so easy if they just said, students, if you haven't paid by this and so date, your name's going to be removed from Blackboard. At that point, you won't be able to attend the class anymore. That would be it. And we wouldn't have all this taking roll from the official class roll and sending people and stuff. If they just send out that email to the students, not to the faculty, to the students, and say, look, if you don't get paid by this date, you're going to be removed from the roll. In Blackboard, you won't be able to attend class anymore. That would be the easy way. That's not necessarily the Lawson way. I'm sorry, I shouldn't say it that way. Okay. Now, where were we? We got down our surface area to be this formula right here. And I believe that's pretty much pretty close to what they've got in the text. They've done some other weird things. But here's where we go from here. How do you do an integral like that? There it is, okay? Well, looks like a U substitution might work. So let's try that. The innermost part of the most complicated part of your problem is this thing right here. So let U equal 1 plus 9x to the 4th. Okay? Always follow the U with a then, let with a then. Then du is equal to 36 x cubed dx. Well, at best, if we pulled that 2 that's out here in here, you would have a 2x cubed. We need 36x cubed. So let's bring another 18 back in there. So let's, in other words, what I'm saying, let's divide both sides by 18. Okay, and then this would be 2x cubed. And we can do that by just bringing this 2 back in here. Okay, so the 2 is no longer out front. Okay, so what this gives us is pi, okay, times the integral. Now we have to change our limits as well. When x was equal to 0 up here, u is equal to 1. When x is equal to 1 here, u is equal to 10. When x equal 1, u is equal to 10. So here are the new limits for u, okay, for u and only for u. And then you have, there's my pen. I couldn't find where my pen went. Okay. What we have now is, oh, I forgot. I didn't put my 1 over 18 out here. Okay, now we have 2 x cubed dx. That's your du. That's supposed to be a u. Okay, and you have u to the 1/2 power. And that's not too hard to do, is it? Pi over 18. And what's the antiderivative of u to the 1/2? Increase it by 1, power rule. That makes it 3 halves, and then multiply by 2/3. Well, the 2 will cancel into 18 9 times. Bring the 3 out, so you get pi 27ths. It seems like they like 27ths. Okay, and then we have, oh, let's see, 10 to the 3/2 power minus 1, because 1 to the 3/2 power is 1. Okay. And yeah, I've already evaluated it, sorry. This is going from 1 to 10. I forgot to write that down. Okay. Now, I don't know what that is right off the top. Oh, I'm sorry, I got lost on the page. I said they're getting a weird answer. It's exactly what they got. Pi 27 times 10 to the 3/2 minus 1. And then they bother to go and see if they can calculate that. And let's see if we can too. See if they got it right. Okay. All right. 10 to the 3/2 power. That's 1, 0. And I'm using the X to the Y key, pressing that. And then my Y is 1.5. 3/2 is 1.5. And press equal. Minus 1. And press equal. And multiply by pi. And divide by 27. And I got about 3.56 and 3.563. That's exactly what they got to. Okay, good deal. So, not only did we do it right, we got the same answer they did. Excuse me just a second. Okay. Now, let's move on to example 7. Oh, wait, sorry. Let's go back to the book, to the PowerPoint, and see how they did the problem. Okay, there was the problem. There was how it looks. Your radius is f of x. Okay, x is going from 0 to 1. Okay, the distance between the x-axis and the graph is your f of x. So your radius of x is f of x. And because f prime of x is 3x squared, the surface area is s is equal to 2 pi times the radius times the arc length. Basically that's it. The integral from a to b, the 2 pi can go on the outside, this goes on the inside. And that's what you've got. The r of x is f of x, which is x cubed. The a and b are 0 to 1. The f prime is 3x squared, but you're going to square that, so it gives you 9x to the 4th. And when you do that, you then get, and what they did, it's absolutely correct, but it's just puzzling how they did it. What they do is a u substitution, but they don't tell you you're doing that. Okay, if you let this be the u without saying it's the u, 1 plus that, and take the du would then be 36x cubed That's what you want here, so then this will be the d of that. So since you're multiplying this by 36, you divide that by 36, which is the same as 1 over 18, which there's several ways you can get there. To me, theirs is a little baffling. It's sort of like you're looking into a crystal ball and seeing that's your answer, okay, without really knowing why. But it is correct, absolutely correct, okay? So that would be pi over 18 times this, and that's exactly what we got. The u, which is 1 plus 9x fourth to the 3 halves power, divided by 3 halves, or multiplied by 2/3. Multiplying by 2/3 then makes the outside to be 1 over 27, which is pi over 27. And what you have then is 10 to the 3 halves minus 1 to the 3 halves, which of course is 1. Okay? And they then give you that as about 3.6563, which is exactly what we got. Good deal. Any question on that? I think the way they do it is just a little bizarre. It's absolutely correct. And if you like doing it that way, by all means do it. It's correct. All right. That was the last slide, but it's not the last example. So let's go back to the whiteboard. If I can get my pen to show up here. And let's clear that drawing. Anyone need that any longer? Okay. Now, the area of a surface of revolution. Find the area of a surface formed by revolving the graph of f of x Well, why does it do this? Go back to the whiteboard. We were there. Okay. Now, I didn't look and see where my pen was. That maybe I did it. F of x is equal to x squared. There's your function, f of x equal to x squared, on the interval from 0 to root 2. Come on, pen. The pen's just jumping all over the place. Okay, there we go. On 0 to root 2. That's the interval for x. About the y-axis, so we're circling around the y-axis as shown in the figure. Okay? Now, that of course is a parabola, and it's going from, that parabola is revolving around the y-axis. Okay? And it's going from 0 to root 2, which on the y-axis is going from 0 to 2. Okay? Now, let me go and write down here if I can get the pen to ever show back up. Come on, pen. Where are you, pen? Ugh, no wonder. Where am I, pen? Okay. About the y-axis. I couldn't remember what word they used. About the y-axis. Okay, that's ugly writing. Okay, now, picture that parabola. Maybe I should draw it. Okay, this is not fun. Actually, what I'll do, doing the parabola, is draw me as close as I can to a vertical line and as close as I can to a horizontal line. Okay, so there's our axis, and let me tick off a few points here and go back to the draw mode, and there would be 1, that would be 2, and square root of 2 was 1.414, so that would be right about here. This is so aggravating. 1.414 is right about there. Okay, now that's 1 and that's 2, that's 2, then here is your parabola, something like this. Okay, and you're revolving this around the y-axis, so it goes to 1 over here and about 1.5 here, so it goes to here and then revolves around the y-axis there and comes back in. That's something like that. It's a pretty ugly drawing. Okay, now your radius of revolution is your x value. This is going back like we did earlier. Okay, the radius of revolution is your x value. It's here to there. That value right there is just x. Okay, now the arc length is still the segment of that. So the arc length, let's go on and figure what that is. Come on, pen. There you go. So your surface area will be 2 pi times the radius, which is x, and x is going from 0 to root 2. And then your arc length is going to be the square root of 1 plus f prime squared dx. Okay. Alright. So, one thing we've got to do is find out what f prime is. F prime, of x is equal to 2x. Okay? That's f prime. And that thing comes on that erases something. I don't know why, but it erased my prime. Alright, so squaring that, f, there it erased my f. F prime of x squared is equal to 4x squared. Add 1 to that and you have 1 plus 4x squared. Take the square root of that and that's what you get. Okay? So, what our function is now, we've done everything they have here. So this is 2 pi times the integral from 0 to root 2 on x times the square root of 1 plus 4x squared dx. Okay. Again, I think a u substitution is the way to go here. Let u equal 1 plus 4x squared, then du is equal to 8x dx. Well, we don't have an 8x dx. We have at best a 2x dx. So what I'm going to do is lose the 2 from here and move it in here. Okay, so we'll divide everything by 4. So this will be a 2x dx here, like it's what we actually have. So that makes the new integral pi times the integral from, now we got new limits here. When x is equal to 0, u is equal to 1. when x is equal to root 2, you have root 2 squared, which is 2 times 4 is 8, plus 1 is 9. And I don't know where my pen, there it went. So this is going 1 to 9. And if we put this over 4, then this would be you would have to yeah, that would be yeah, it's just a du here. So this is the square root of u du, because the du over 4, the over 4 goes out here, and the du is this thing right here. Sorry, 2x dx. That's your du, and then you have the square root of u is this part. Okay, so this is u to the 1/2. I don't like writing it as square root of u, so I'm going to erase that ugly square root. I erased way more than I wanted to. Okay, and what's that integral? Pi fourths out front, antiderivative of u to the 1/2 is u to the 3/2 times 2 over 3. This 2 will cancel into that twice, so you have, I'll get to it in a minute, and this is going from 1 to 9. Okay, so this is going to be pi 6, because the 2 will go into 4 twice, 2 times 3, pi over 6. And then we'll do the evaluation here. Square root of 9 is 3. 3 cubed is 27. So that gave us a 27. Come on, yeah. 27 here, minus, and square root of 1 is 1, and 1 cubed is 1, so it's 26. So this would give you, and 6, 2 will go into 6 3 times, 2 will go into 26 13 times. Okay, so you get 13 pi over 3. Okay, that's what I got. 13/3 pi, that's what they got. Now, if you want to do the calculator just to see if you get the same answer they did, all right, got to turn it sideways to get it to come up, and that would be 13 times pi divided by 3. That gives about 13.614. Yeah, 13.614. Got the same thing they did. It's approximately equal to 13 point. How they get that many digits, I don't know. 614. Okay. All right. Any questions? That wraps up then, folks. 7.4, finally. Homework exercises in 7.4 would include number 5. It should be at calcchat.com. Any of the odds 7 through 19. They should all be at calcchat.com. 7's at calcview.com. And you could break those down into 7 or 9 with both the Calc Chat and 7's at Calc View, and then any of the odds 11 through 19 all at Calc Chat. Then any of the odds 21 to 29, and they say that you might need graphing utility to approximate the arc length. If you do need that, use one. If you can't get it, go, but most of them you can figure out. 31's an approximation a lot like the one that we did in class earlier. No, this is an approximation. Number 33 is a lot like the one we did in class earlier. It should be at Calc Chat. 35 should be at Calc Chat. 37 should be at Calc Chat. And then either any of the odds 39 to 43 should all be at Calc Chat. 39's at Calc View. 45 and 47 are at Calc Chat with 45 at Calc View. 49's at Calc Chat. 51 and 53 you can explore the concepts there. If you aren't particularly good at that, you can skip them, but they should be at Calc Chat, so that would be a good place to sort of get a clue of what they're looking for. Then they have number 55. You can think about doing that one. It should be at Calc Chat. The C part, they indicate you might need a graphing utility. I'd say either 57 or 59. They should both be at Calc Chat. 61 should be at Calc Chat. It may require a graphing utility. And 63, volume and surface area, should be at Calc Chat. 65 and or 67 should be at Calc Chat. 69 and or 71 should also be at Calc Chat. Okay, good deal. Hang on just a moment. I need a sip of something. My throat is dry. All right, now we're moving now to 7.5. So let's go back to our screen share, and I think this is 7.5 here. It sure doesn't look like it. Let's go back. I had it up here, and now it doesn't seem to be here. So let me pause for a moment here. Well, I think I hate to do this, but the only thing I can see that I can do now. Let me close that for a moment and stop sharing for a moment. Now I can see it. There's 7.5. I knew I had it up here. All right, so let's close that and go back to screen share and pull up. Okay, where is it now? That's still 7.4. Okay. All right. It's so frustrating. Where is 7.5? That's 7.4. Let's see if any are missing here. Maybe I can get it this way. All right. Now let's see if it will. There it is now. Goodness gracious, what a pain in the neck. Or some other body part. Okay, we'll go from current slide. Screen sharing is paused again. Let's go back to 7.5. There it is. Okay. Now we'll go slideshow, current slide. Man, they make it difficult. Okay, can y'all see Chapter 7, Application of Integration? Yay or nay? Can you finally see that? Okay, good. Now I've got to do all this messing around again, moving this out of the way. You can't see what I'm doing, but it blocks me from seeing the screen. All right, applications of integration, that's Chapter 7, 7.5. I have to touch the screen before it'll open, is work. Okay, y'all didn't want to work any today, did you? Okay, objectives here are find the work done by a constant force. That's a piece of cake. You probably already done that in physics sometime in your life. It's really easy. Finding work done by a variable force, that requires calculus. Okay, so let's start with the easy part, work done by a constant force. In general, work is done by a force when it moves an object. If the force applied to the object is a constant force, then the definition of work is as follows. And this is almost straight from physics. If an object is moved the distance d in the direction of an applied force F, then the work done W done by the force is defined as F times d, the force times the displacement. Okay? Now, a couple things in there. Object moved the distance d in the same direction of the applied force. If they're in the same direction, it's just, and if the applied force is constant, then the work done is F times d. Now, one thing that's sort of buried in there, if you don't move something, you're not doing any work. Now, I usually give the example of our patio. When we first moved into this house, the backyard slopes downhill toward the house, and then the front yard continues and slopes downhill toward the road. Well, some previous owner had built an extension on the back of the house and dug into the hillside and put the extension there. So that meant in the back of the house, the soil came right up to the bottom of the windows, okay, on the inside. You know, the soil was on the outside, but the bottom of the windows, and they were squatty windows. So it really looked a little strange, but I didn't like the way that looked, because not from the aesthetic viewpoint, but because water coming down the hill was going against the back of the house, that new extension on the house. And, you know, hydraulic pressure will create some issues over time. And number two, they had the soil right up on right below the windowsills, so there was wood to ground contact, and if you're anywhere in the southeast, you have a problem with termites. Now, I'm sure they use treated lumber, so far there hadn't been any problem with it, but it still was, over time, the moisture against the house was going to leach out the treatment in the wood, and the termites were going to come in. So I said to my wife, well, if we get this house, you know, she thought it looked a little squatty in the back, but otherwise she loved the house, she loved the lot, she loved everything about it. The price was a little high, but we were able to get that down a little bit. But anyway, I said, you know, we're going to have to do something to get the water away from the house and to get the level of the soil down away from the wood. She said, good, I wanted a patio anyway. Not exactly what I had in mind, okay? So for the next, and it just happened to be that summer, I only taught for the first 5 weeks. We were on quarter system then. The first mini-term, I taught 2 classes in automotive math, and the second mini-term, the next 5 weeks, I had off. They didn't have enough work for me to cover that second mini-term. So I got started sometime in that first mini-term getting set up, and for most of the next 5 weeks, I dug out the patio, okay? It was not fun. It was a hot, dry summer. The clay in the backyard was hard as a rock, but then in addition to that, there were actually rocks in there. If you dug anywhere around the Birmingham area, you're going to hit rock pretty soon. There was this one boulder that I ran into, completely covered with soil. It was about 4 feet tall, and it was about, I couldn't get my arms all the way around it, okay? So it was a big boulder. I could get them a little over halfway. I didn't hug it much, but yeah, it was about like that. And I dug, and I yanked, and I pushed, and I pried. I used cheater bars and everything I could think of. I could not get that rock to move, okay? Now, by the formal definition, though, all the effort, all the force, all the grunting, all the straining, I was doing zero work, because work, by definition, is force times the displacement. If I didn't move the rock, I wasn't doing work. Don't tell me that on that hot summer day when I was doing it. But anyway, that's how we define work, okay? There are 4 fundamental types of forces. Now, why in the world do they get into that here? I don't know. Again, this is straight from physics, and it has almost no bearing on anything here, but this is absolutely true. There's gravitational force, which is a relative weak force, but it operates over a long, long distance, okay? You have electromagnetic forces, which tend to be stronger than gravitational forces, but they don't have nearly the range of field. Then you have strong nuclear and weak nuclear forces. You'd have to get into nuclear physics to understand the difference there, but I'll just give you one example. Okay? Electromagnetic forces, like I said, are pretty strong. But if you picture the nucleus of an atom, the nucleus of an atom is made up of protons and neutrons. Every proton in there is positively charged. Every one of them. And for big molecules, that's a lot of big atoms. There are lots of protons. And they're in a very tiny little space. The neutrons are in there, but they have absolutely no charge at all. The electrons are flying around on the outside. Those are the negative charges. What's holding those protons together? Obviously, electromagnetic forces are not, because like charges tend to repel each other. They should be blowing apart, but they're not. Therefore, there must be some fairly strong nuclear forces that hold atoms together. And that's about the extent we know of those now. Nuclear physicists probably have a little bit more understanding, but it has to be an awfully strong force. But they're over incredibly small distances, okay? Because it doesn't yank anything else in, it just keeps the nucleus in place. So, why that came up, I don't know. Go back to forces. A force can be thought of as a push or a pull, okay? A push or a pull. A force changes the state of rest or the state of motion of a body. That is, if it does push or pull. If you push against the wall and nothing happens, you're not changing any state, okay? But if you are able to create motion, that's what force does. For gravitational forces on Earth, it's common to use the units of measure corresponding to the weight of an object, okay? Now, that is a weird way to express it. What they're basically saying, weight is the force. The force due to gravity pulling something downward, that is the weight of an object, okay? Now, example 1, pretty simple. Determine the work done in lifting a 50-pound object, that's a force, 50 pounds, weight is a force, 4 feet into the air. Well, the weight is being pulled downward by the force due to gravity. You're lifting it upward. That's in the same direction, just in opposite direction, but along the same line. So what is your work done? I don't even have to go write it. Force, 50 pounds, times distance, 4 feet. That would be 200 foot-pounds. That's how we measure work in the U.S. customary system, 200 foot-pounds. That's all there is to it, 200 foot-pounds. Magnitude of the force required to lift the object is its weight, okay? And you're lifting it 4 feet into the air. Oh, hit the wrong button. And that gives you 200 foot-pounds of work. If you had pulled on that with, say, 45 pounds and you couldn't lift it, you could pull on it with 45 pounds till the cows came home. If you didn't lift it, you were doing no work. Even though you may have been sweating and all sorts of things. Nope. Until you move it, you're doing no work. All right. In the U.S. measurement system, work is typically expressed in foot-pounds like we just saw. You could use inch-pounds, foot-tons. You could use anything that multiplies a distance by a force. In the SI system, the basic unit of force is the Newton, and then a Newton times a meter would be, well, a Newton is the force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram. So in that system, work is typically expressed in Newton meters, which is also called a joule, named after James Prescott Joule. There's a few names that you can use for paper topics. Hint, hint, get your paper topics done. And that's those units. I think we just ran out of time, but let's do this one other. In another system, the centimeter gram second system, the basic unit of force is a dyne. Okay, it's not used very much in physics anymore, but for smaller measurements, a dyne is a force in the metric system, is a unit of force in the metric system, and a dyne centimeter is called an erg. Okay, so that's it, the energy measurement in the CGS system. All right, and that table talks about all three of those. Okay, and it gives some sort of conversion factors. So it's pretty good for a math book to give those kind of informations. That's on the bottom of page 485. Okay, we'll start next time with work done by variable force. Okay, now, did we get far enough for you to do any homework exercises in chapter 1? Yes, you could do either 5 or 7. They're both at Calc Chat. 7's at Calc View. Okay, those are with constant forces. All right, so that's it for today. Any last thoughts, parting shots, questions, anything before we leave? Remember, folks, if you haven't completed your payments, please get that done immediately, if not sooner, because at some point pretty soon they'll probably remove your name from the Blackboard, and once your name's no longer in Blackboard, then you won't be able to log in anymore. So please get that done. Okay? Any questions? All right. We'll be ending the slideshow then, ending the Zoom meeting. We'll see you on Monday. Have a good weekend.